organizers for having me, and also thank you for putting me last. That way, nobody's going to argue with me. Everyone's too tired. And also, my talk is going to be... That was bait. I knew you would argue with that. But okay. But also, my talk will be the most memorable due to peak and rule. So thank you for that as well. So in my lab, we're interested in sort of people's common sense reasoning and intuitive physics, as you'll hear about, but also intuitive psychology, which I'm very happy to talk about as well, but not in this talk. I realized, by the way, part of the problem of hearing excellent talks, including ones like Andrew about gesture and Shimon's about hands, is that I don't know what to do with my hands now. I become sort of hyper-aware. So I'm interested in intuitive physics and intuitive psychology, but we can talk about it later, right? Anyway, where was I? Here. Where am I going? Here. So this is the roadmap for the talk. I'm going to give you sort of the spiel of what I'm going to talk about, which is approximations in intuitive physics. So we already heard why you should care about intuitive physics. I'm going to take that as slightly read, but you really should, whether you're in cognitive science or AI, but that's partly read. And I loved what Kelsey was saying about you don't want pixel perfect, you want physics perfect. I would amend that to you want physics okay, not physics perfect, at least for people. If you're building a rocket launcher, sure, you want physics perfect. Not intuitive physics. But for people, physics okay. That's going to be the spiel that's underlying these 5 things that are going to come at you pretty quickly. It's going to be rapid fire, kind of like a Rocky training montage, right? Except instead of chasing chickens and drinking eggs, I'm going to show you some science. Okay, so people are ready for that. And if you're ever kind of, again, it's the end of the day, if you ever find yourself like slightly losing attention, things like that, every one of these is built modularly. You can sort of jump on, jump off, mostly jump on, of course, but if you ever sort of like lose the plot, you can jump back in, safe in the knowledge that while these things seem kind of different, they're telling the same story. And what story is that? Okay, well, let's get to that. Intuitive physics is cool, as we know, right? Just the fact that people are able to reason about the everyday behavior of everyday things. People can reason about how things bounce and drape and crash and smash and schlorp and glurp and other terms that I made up. And they do this, okay? So there's like a whole science about describing the fact that they do this, but for us, it's interesting to ask how they do it, right? People have spent $1 trillion and billion of PhDs to figure out how I know that this is a microphone. But we're interested in the computations that allow you to reason about how this microphone is going to behave. God forbid, should I throw it at someone, right? And the suggestion from a lot of people have been that the way that people reason about a lot of intuitive physics is by running something like a mental simulation. So all these things look visually very different, but they were created by very similar programs. The same program created all of these things, and the suggestion is maybe some people are running something like that program in their head, where like is doing a lot of the lifting here. A priori, even if you didn't have any data, there would be reasons to think that this is a good idea to put into an organism, something like a mental simulation, because if you have the right mental simulation, you can do prediction, you can do inference, you can do generalization. And there have been also empirical arguments suggesting that people are doing mental simulation. And you kind of heard it. It was slightly taken for granted in the other talks, but there were questions about it, rightly so, from the audience. And I want to stress that not everyone is la-di-da about the idea that people are running something like a mental physical simulation. There are the naysayers, or to put it in a technical term, the haters. And the haters think that we're not running mental simulation. And a lot of their arguments seem to be about, by the way, very good, smart haters, okay? So but a lot of their arguments seem to be about the fact that, well, let's suppose a perfect simulation, and then we show that people deviate from it, ergo, people aren't running a mental simulation. I'm oversimplifying, but you can see why the counter to that immediately is like, well, of course, people are not running a perfect simulation. They're running a coarse simulation, of course, right? It's late. I need to rely on these kind of little tricks, right? Okay. But that's not enough, right? Like, even if you think that people are using something like a coarse mental simulation or approximations, I'm on the hook as someone who's claiming that to say what approximations specifically people are using, and can you show that that's in fact what they're doing? But again, the argument is something like the following. Okay, so people who build simulations that are supposed to run in real time, in reasonable time, to produce results that are reasonably okay for something like, let's say, video games, are also not trying to create perfect simulations. They're under a lot of constraints of memory and time and things like that, and computation, and so they use hacks. And I don't mean hacks in the sense of breaking into other people's computers or the obscure falconry code, for hawkheads among you. I mean hacks in the sense of clever workarounds. And so for us, we were interested in looking at these sort of workarounds that engineers have come up with, who neither know about nor care about cognitive science necessarily, and say, well, if the mind is under similar constraints to get things running in real time and get kind of okay things looking kind of okay in its simulation, maybe there's a kind of conceptual convergent evolution that the mind arrived at something similar to these approximations. So we can use the approximations we see in simulators as starting points. It's not proof. It's a starting point for an exploration to see whether people are using this kind of thing. Would you like to know more? Sorry, that's one of my favorite Starship Troopers. Would you like to know more? Read that paper that Toby was talking about. Okay. So now the people are on board with the plot, more or less. That's the logic that's undergirding these projects that are coming at you. So these are different approximations, but they all have the same kind of logic. Approximation number one: what if instead of needing to know that this is a microphone, I'm going to throw it, right? Not at you, but it's, over there. Where is it going to land? Don't worry, it's not happening. I'm terrible at intuitive physics, actually. All research is me-search. It doesn't really matter, right, the particular perforation of these things over here. I kind of maybe just need to put a cylinder on it. And indeed, this is, right, I'm highlighting sort of the people who did a bunch of the work on this. Indeed, you find that in a lot of simulators that engineers have come up with to make your video games work, the entities in these game engines lead a kind of Cartesian dual life. Right? Like entities such as this ducky have both the things that you need, the properties that you need in order to trace out what this image looks like, to render it onto the camera. And for that, it really matters that, exactly the texture and the color and the lighting and things like that. But to know if this ducky is going to collide with that ducky, the game engine actually has a different approximation to keep track of where things are and are they going to collide with one another. And for that, it really doesn't care about all of those things. So this is a distinction that exists in nearly any game engine that I looked at, 2D, 3D, whatever you want. This distinction between shape and body, where the shape is the carrier of the information for the rendering and the body is the carrier of the information for tracking in physics and things like that. Are people using something like this, right? What if people are using something like these approximate bodies for planning? How would we find out? Well, we need to design these psychophysical experiments that will tease apart cases where the body is the same as the shape. And again, you can imagine all kinds of approximations, by the way. When you start to say, like, maybe there's an approximate body, you can think of it as like, maximal approximation is maybe like a bounding box, and then you kind of take the air out of the shrink wrap until maybe the body is the same as the shape, in which case we would say people are not using an approximation. So are people using something like this approximation? Which ones are they using? We'd like to create situations in which it's the same shape, but the approximation would predict sort of different distances between these bodies. So for example, one of the situations used was Michottian launching. This was mentioned in the talk 2 days ago, but do people here know? Who here knows about Michottian launching? Raise your hand. Who here doesn't know about Michottian launching? Raise your hand. Okay, we're doing some interaction, Toby style. Okay. So in Michottian launching, you have an agent, and the agent is moving, and then it comes close to a patient, and then let me just show you. Forget it. Okay, here we go. Okay, look at this video. So the agent is the thing that moved first, and the patient is the thing that moved second. And now my question for you, watch this again, okay? And just raise your hand to the degree that you would agree with the sentence. Raise your hand to the degree that you agree with the sentence. The agent caused the patient to move. Okay, I can roughly say what that's like. This has been studied for decades in psychology. There's a very nice psychometric function that says that, like, when you see things like this, people strongly agree that A caused B to move. When you see this, like, the greater the distance, the more the drop-off in the perception of causality. And also there's timing differences. So there's a very nice drop-off in the perception of causality that we can use to our advantage, because we can have two shapes that have the same distance between them in collision, the same effective distance, but if you're using an approximation, there's a different distance between the approximate bodies. And we predict and find that indeed these kind of collisions are going to be seen as more causal than those kind of collisions, right? Quantitatively, qualitatively lining up. And we can in fact use this mathematical approximation called alpha shapes to work backwards, and from the data think about what approximation is most likely that people are using. And it's not a convex body, and it's not the same as the shape, it's somewhere in between. And there's a bunch of these psychophysical studies, including change detection and time to collision and things like that. Transition. I warned you that this is rapid fire. Okay, so if people want to talk more about that, I realize that that was fast. Probably there's a lot of details you want to know about. Let's talk about it in the lake. Here comes another thing, which is about partial simulation. And this is work with Lonnie Bass and Kevin Smith and Elizabeth Bonowitz. So the idea is as follows. Do you remember the haters? the people who say that we're not using mental simulation at all, they have really good arguments. And one of their arguments goes as follows. If you were using something like an engine, then these things are capturing reality. And reality obeys probability. Engines should obey probability, and so people should also obey probability in physical situations. Including, this should obey the conjunction law. The probability of event A should be equal or greater to the probability of A and B. People agree with this, presumably. And what if we find something different, okay? What if we show people, like this very clever experiment by Ullman et al., we show people these sort of, they show these movies of these balls moving around, and we ask them about the probability of different events happening, like the event G, which is this pink sphere ending up on the grass, and the event H, which is the cannonball hitting the sphere. And you show people lots of videos, and you ask them lots of questions about the probability of those events, and they do very careful work to like validate that people understand the probabilities and use them correctly, and they find that overall people think that the probability of the sphere hitting the grass is smaller than the probability of the cannonball hitting the sphere and the sphere hitting the grass. You see why that can't be, right? This is a conjunction fallacy. Surely this should be greater or equal to that because this is part of that. Great, so, and those of you, by the way, who know conjunction fallacies and like Kahneman and Tversky, we heard their name mentioned, right? This was a huge deal with Linda, the feminist bank teller. So this is a conjunction fallacy in physical reasoning showing that game engines are dead, physics engines are dead, and the conjunction fallacy killed them. Except, right, this is relying on the notion that we're doing a perfect simulation. What if you're not moving everything in the scene? What if you're only moving some of the scene, okay? So you can derive the idea that what if I'm only moving this ball, for example, neglecting entirely this cannonball over here? Now the probability of this thing ending up on the grass, well, it depends if I'm moving this thing or not, right? It's a very simple addition to the simulation model that I think is quite reasonable, and it's an open parameter that we could potentially fit to the data, and it leads to a simple equation of the probability of all this stuff happening that I'm not going to get into, but it's high school math. And this model, which is very simple and obvious, leads to some very non-obvious predictions. It says that depending on where you place this sphere at the beginning, you're going to get a U-shaped function where the y-axis is the amount of the conjunction fallacy, where above 0 means that there is a fallacy and below 0 means that there isn't a fallacy. Okay, and you can, anyway. So it's going to be a U-shaped function, and it's going to move up or down depending on what the trajectory of that cannonball is. It's not obvious, it just comes out of the equations. And I want to stress, by the way, we just, you know, kind of like what Toby was saying, I wish I had the whiteboard for this thing, because like we drew it out, this is the model, and we registered everything, right? We pre-registered, wrote down everything that we think is going to happen. I was never so scared in my life, that's a lie. But I was very anxious to see what we would find, and it just lined up beautifully, right? Qualitatively, quantitatively, like the degree of agreement between people and the data was astounding. You see that we replicate Ludwig et al. They were right. You do find a conjunction fallacy in this regime, but you can make it go up, you can make it go down, you can make it go away entirely. This is not obvious at all, except, and anyway, it lines up in this way. And I want to emphasize, again, this does not negate what Ludwig and Piri found. It just shows that when you're using an approximate simulation, in the sense that we mean here, you get these kind of effects. I'm not, you know, partial simulation is not a fallacy per se. It's not necessarily something you want to build into your models, by the way. Those of you who are building rocket ships, please don't build in partial simulation, but it seems to be something that people might be doing. Transition. You want to know more? Let's talk in the lake. Let's move on to something we call non-commitment. So a lot of these things that we were talking about so far were the idea that we're getting some perception. And not just, we don't need to care just about recognizing the object in the sense of its perceptual properties to recognize that it's a ducky or a microphone or things like that, but something like its rough body and, you know, how do we keep track of these things and these perceptual questions and things like that. These projects over here are moving a little bit more into sort of imagery and imagination, the kind of, instead of the perceptual side, bottom up, sort of more top down. This is a project we're calling Non-Commitment in Imagery with Eric Billow and John McCoy, and it asks a simple question. Here comes some more audience participation. Okay, so I'd like you to imagine a scene, and then I have a question for you. Is everybody ready? Okay, so a little bit of effort. Here we go. Okay, I'd like you to imagine a person walking into a room and knocking a ball off a table. Okay, people try to imagine it. Right? Okay, here you go. You have it in mind. Does someone here have aphantasia, by the way? No, it's unable to create visual images. All right. Anyway, all right, great. So now I have some questions for you about that scene that you saw in your mind's eye. And please pay careful attention to my question, because it's not, I don't want you to recreate the things that I'm asking you about. Okay, I just want you to say, for the scene that you had in your mind, kind of freeze it, and then I want to ask you about some properties of that scene, and I want you to tell me, was this property part of your scene at all or not? Was it something that you didn't bother thinking about? People understand the game? Yep. Okay, great, thank you. The color of the, so sorry, raise your hand. You know what, sorry, yes or no. Let's do yes or no, okay? The color of the ball.
Yes.
No. Yeah, sorry, I mixed you up. Let's do this yes or no. Okay, so the color of the ball. Okay. The gender of the person.
Yes.
The clothes of the person.
No.
The size of the table.
Yes. Yes.
The trajectory of the ball, you can sort of do it with your hand.
Yes.
The relative position of the person to the ball.
Yes.
The size of the ball.
Yes.
We can keep going like this, okay. But this is quite interesting, and it has to do with this question, the imagery debate of when you imagine something, do you actually see a picture, and is that picture playing any sort of functional role? And people before have pointed out that it's interesting that even when you imagine things, you can't answer certain questions that would have been trivially easy for you to answer had you seen the scene of a person knocking a ball off a table. And so we ran this with lots of people and found that just the percentage of people saying it was not part of my mental image, for any question that we asked, some significant number of people said this was not part of my mental image. Is an interesting thing, first of all. But also, it wasn't uniform. It's not like people have some finite amount of juice that is randomly splashed in terms of paint on the picture. The person's hair color, many people said it wasn't part of their image. The person's height, the table color, nearly everyone talked about the ball size or the table shape or things like that. And we did this with many other scenes, by the way, and they all sort of say the same thing, right? Like we did this with lots of other themes, bunch of other scenes, bunch of other properties, and they all have this point, which is it's not zero, it's not random. And if you look at the kind of properties that people seem to care about, for me, at least, it jumps out that a lot of people can report or say, like, the things that they care about is the relative position of the things, spatial properties and things like that. Color, material, texture, things like that. If you're imagining a sort of scene construction algorithm, right, you're the Disney animator, right? It doesn't seem to work like Disney animators are doing something like, someone comes up to the animator and says, the boss comes to them and says, I want a new movie. And in this movie, it should be a hedgehog riding a bicycle. And it's like, okay, boss, I'll get on that. Right, and they don't start going like pixel, 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 right? Like when they're animating these things, God forbid, right? They start, okay, the hedgehog will be over here, and the bicycle will be over here. It's like, are you done yet? Like, no, hang on, boss. Like, I'm getting there, right? But you create the asset of the hedgehog and the bicycle. And it's like, what color is the bicycle? I don't know, right? Like, give me time. It's a hierarchical scene construction process, and it makes sense that some of these properties are not things that you bother thinking about at all, which is, by the way, somewhat different than the way that we're seeing DALL-E 3 and these other systems doing it. Transition, 2 more. Okay, how are we doing for time, by the way?
5-ish.
Oh my God, okay. I clock it at 7. Okay, sorry. It's okay, 5 or 7 will be fine. All right. So, next project, this is about visual pretense and physical properties, following on the importance of these approximate bodies and scene construction having to do with things like shape rather than material and stuff like that. This is with Pang Xian. This is Snoopy on his doghouse, except of course he's a pilot. This is my daughter. She didn't know about Snoopy. I just love that image. And this is outside the airport in Vienna, called The Flight of the Imagination. All right. So let's build some intuition for this thing. Again, it's audience participation time. Look at this. What is this? A block. Okay, so everyone, 1, 2, 3, it's a... Thank you. Okay. But let's suppose it's something else. I'm going to pretend, does it make more sense for me to pretend that it's a car or a strawberry? Who thinks car? Raise your hand. Who thinks strawberry? Raise your hand. Cool. So that's what a lot of this was about. We're asking about people's intuitions in this kind of thing that we're calling visual pretense, which is the thing that is found in childhood, but also a lot in adulthood when we're telling these narratives, right? I was over here, and the truck was coming from here, and it nearly hit me, blah, 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 blah. Shows up a lot, and in this kind of visual pretense, right, it's not that any intuition possibly goes. So question number 1 is, will people have a systematic pretense in how they do systematic preference in how they do visual pretense in the world when they imagine this to be something else? And this question kind of requires you to have soup for brains, because of course there's going to be that kind of thing. But philosophers with soup for brains, but say, well, look, pretense imagination is all about departure from reality. The whole point is that you're saying that something is not what it is. But there will be a preference. That's not so much what we're interested in. What we're interested in is what determines that preference. And our hypothesis is that some visual pretenses are going to be systematically preferred. These are going to be determined by a hierarchy of features. And in this hierarchy, physical and spatial features are going to be more important than surface level features of the kind that a lot of machine learning cares about. And current machine learning models that care about things like surface level features will not capture this pretense. So we ran 4 experiments. The first one is basically the block is a strawberry or a car kind of thing, right, where it matches on surface level properties or shape level properties. And we did this for many real world objects and many things. I'm not, because I'm short on time, I'm going to basically say physical properties win at matching what people are doing, surface level properties don't, and the current machine learning stuff like CLIP and stuff like that, where you embed things in high dimensions and say, is it closer, is this image of the car, of the block, closer to the concept car strawberry, fails completely. We did this for both things that we came up with, also freeform pretense. It all makes the same point. We also did some stuff on alignment. So it's not just that, if I ask you to pretend, that this is an elephant, you don't just take this away and replace it randomly with an elephant. You probably have some subparts that you're trying to align. So can people point to the trunk of the elephant?
Yes.
Can people point for a second? Oh. Okay, so I'm going to pretend for a moment that I collected your data in real time, and I'm guessing most of you pointed either over here or over there. We can compare this to kind of a filling in model, and if you do filling in, this is an elephant, it does this stuff. I'm guessing none of you imagined that kind of thing. Why would you? And we did a bunch of work showing that, of course, people align the subparts, which is very similar to Ovid's metamorphosis. Great. Is it 2 more minutes? Okay, 2 more minutes. Here we go. Last thing, which is very fun. All right, we're nearly there, everybody. Ready? We're going to talk about capacity limits of mental simulation. So you heard about mental simulation. You might know about some of these things already of people can imagine the Jenga blocks falling and Toby's work on the balls and things like that. But there's a question for us about, well, when you're keeping track of these objects in your mind's eye, how many can you move at once? Right? This isn't about the third project I showed you, where partial simulation was just, there's some things I don't move at all. When I'm moving stuff, how many of them am I moving at the same time? And this is work with Hilali Balaban. You'll notice the slides transferred truly into dark mode. We are through a glass darkly. So welcome to the dark side, Emperor Palpatine, but we will be talking about not unlimited power, but limited power. Some of you might be getting vibes of multi-object tracking, right? There's much, much, much work in cognitive science about showing you sort of balls moving around and seeing how many of you can keep track of in direct perception, and the number is something like 3 or 4, depending who you ask. We're asking, if you want to think of it poetically, how many balls can you keep track of in your mind's eye? And the way we're going to do it, this is the last audience participation, I'm going to show you this movie of a ball moving. And whenever you see a ball moving on the left-hand side, please humor me, it works, okay, if the audience does this. When you see a ball on the left-hand side hitting the ground, when you see it hitting the ground, you will stomp your left foot, okay? People are on board, ready? So the ball is going to hit it. Here we go. Thank you. And when you see a ball hitting the ground on the right-hand side, I'd like you to slap your right thigh. Okay, people are ready? Here we go. Thank you so much. Okay, so that was in perception. We're going to do an imagery task, okay? We're going to see a ball moving. I'm already telling you that it's going to be on, I think it's the left-hand side, so get ready with your foot. And it's going to pause. And I want you to continue it in your mind's eye and stomp your foot when it hits the ground in your mind's eye. People are ready? Okay, here we go. Excellent. That's the first experiment, okay? We showed people these 60 movies of balls and different trajectories and things like that with different true impact times, and people do it really well, okay? So they're very good at doing this, and it's true for the individual data. It's all good. Now we're going to do it for 2 balls. And you can imagine that your mind is simulating 2 balls at once, in which case the reaction time for 2 things, bless you, should just be a superimposition. The imposition of 1 ball, one on top of the other. But you could also imagine that your mind is taxed and you can only move 1 thing at a time. You have 1 core in your simulator, and it needs to move this one, and then it goes and moves this one, leading to some very predictable, very big differences in the reaction time, okay? So these are predictions of the 2 models that we build, the simulators, and I'd like you to try it on yourself. So here are going to be 2 balls. Okay, so get ready with your stomping and your slapping and things like that. Ready? So again, the goal is to stomp and slap according to when these balls hit the ground. Here we go. That's what we're looking for. We measured laughter. Okay, one more. Ready? Okay, so we did this again, many movies, many things, blah, 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 and the results are this. Serial model wins out by a landslide. And we did all sorts of controls that I can tell you about if you want. This is, by the way, true for at every individual level, okay? So there was no participant that could suddenly do 2 or something like that. Lots of controls that I'm not going to tell you about. The bottom line is, how many objects can we simulate in our imagination at once? 1, give or take. All right, and so where are we? We are done. We're done for this, and we're done for the day. Here's a summary of where we were. And again, the point is that intuitive physics is important. Maybe we're using something like a mental simulation. The mental simulation isn't perfect, so what sort of approximations are people using is an interesting and useful thing to think about, and I think also very useful for cognitive science and AI, potentially. All right, with that, I'm done. And I know that there's a discussion coming up, and we're already running pretty late, so I don't know how many.
Fine, let's take a few questions. Yeah.
All right, sure. Yeah.
So, yeah, very interesting stuff. For that last experiment, I wonder if you did the eye tracking, because both the talk and the one before, I felt like eye tracking would play a big role. That mental computations you're doing are very much related to your eye movements. So, like, even when the ball was not visible, like, I was still moving my eyes.
Yes. Yeah. And so it's interesting because, like, in some sense, in the mental simulation models, it's not a necessity, right? We don't have to have like an embodied eye keeping track of these things to do that. I agree with you that it would be very useful to do that, and that's why Hilali is gearing up to do that. I wish I had data to show you on that, but I do not. I'm sorry. Yes.
Maybe just a brief follow-up on that. I mean, it was quite a difficult task to get the timing, but I felt like if you were alternating, as you would in the real scene, between the two, you'd ask me where did they both end up. I might have been able to do that, so I could move the two maybe, but couldn't give you the accuracy that the task required.
So, sorry, let me make sure I understand the question. You surely can tell me where they'll end up. That's fine, right? Like both the parallel and the serial simulation models can tell you where the balls end up. So if we just ask people where they end up, that's not telling us whether they're doing a parallel or a serial simulation.
Okay, right. So what you really care about is how many you can move in parallel.
Yes, so we care.
How many I could move at all. So if you did 6 balls and said where would they end up, I'd probably then you'd hit the pile of Shiren kind of limit, right? Like, well, I could tell you maybe 4, but not more than that.
Potentially. So we're finding, but the limit we're finding is even stronger than the Peletian one, right? Like for them, it was something like, well, depends which part you care about, right? Like there's all this work in multi-object tracking that says that we're keeping track of 3 or 4. And we started this project perfectly thinking that we might hit something like 3 or 4. We were surprised that it was 1, right? So that was quite surprising, but the results are very strong. But
some parallelization, right? I feel like I'm thinking about them both and I'm alternating between the two.
Well, that's not parallelization, right? Like that parallel. There's the sense of like it's not that the other ball it's not that the other ball, by the way, disappears from memory. If it disappeared from memory, you wouldn't know what to do with it at all. But you're able to solve the task in the sense of doing one and then the other. What we're saying the capacity limit applies to is how many you're simulating. So again, by comparison to game engines, right? If you had a game engine, the game engine doesn't forget about the other bodies when it's moving the bodies, but it's moving them in certain orders and things like that. So we're asking about like what are the limits of the simulation, right? And by the way, there's work in multi-object tracking that suggests that the tracking seems to be about 3 or 4, but you're not doing sort of forward trajectory tracking more than 1 at a time. But
yeah, so this is a very great talk actually. So 2 questions. So not commitment, pretense preferences. What's the sort of impact to those of us who want to sort of leverage what you're saying for AI, I guess? I mean, the other ones I sort of get, but for those 2, I'm not quite clear what they
So for the visual pretense, for example, yeah. So I think for both the visual pretense and for the non-commitment, okay, I'll just go ahead. As I mentioned, like our current best models for reasoning about image detection and things like that don't do well on the visual pretense stuff. They don't capture what people are doing. Now, maybe you don't care about what people are doing, but to me it suggests that, going back to what Dan Yeamans was saying as well about mid-level representations, that we have these mid-level representations that are very useful, like these approximate bodies, right? That are very useful, for example, when we're engaging in visual pretense. And this is one example of how people use it, but it's suggestive that something about our image recognition models, if they're not taking into account these spatial properties, they might be on the wrong path. Now again, I don't know, do you want to leverage that? That's somewhat up to you.
And non-commitment, what's the takeaway there?
So non-commitment, that's interesting. Again, to me, what the explanation for non-commitment is that this is suggesting something like a scene construction process that you can stop at some point, right? And for that, you can just use that to answer a lot of questions. So if you're building a machine that is supposed to give you answers about stuff, it doesn't have to go all the way down to a rendered image in pixels and things like that. And the way that it works is not like these models that go down to pixels, let's say.
So you presented a lot of evidence about sort of simulation as a cognitive capability. My question is, what hard evidence do you have that this is actually utilized in the motor system? So, because these are two separate things. I mean, not necessarily they are the same, right? For example, I mean, I'll take an analogy in vision, like going back to the 70s and 80s, we have this stuff on the what versus where pathway. So Melvin Goodale had these, studied these patients of this woman who could insert that object into the and she knew her motor system knew how to do that, but she could not describe this as a shape thing.
Yep.
So here it could be that you have this capability, it enables you to make sense when you're watching videos, you're good at predicting that, but your motor system is not necessarily making use of this. I mean, you would have to prove it.
So,
I want to know if you have experimental evidence.
So au contraire, I would say that it's not just that the motor system is using it, I'd say that it's the primary one that's using it. So first of all, there are other, not just mine, but there are other experiments that ask people to interact with things in terms of, if you mean the motor system in the sense of moving your hands to catch stuff, some of these experiments rely on exactly that. And in fact, it only works if you just ask people, about drawings. You show people something like this drawing and you ask them like, here's a pail and a pendulum or something like that, and it's swinging. Where do you think it's going to go? They're terrible at it. But if you have them move something to try and catch it, they follow the predictions of a simulation engine. But I think in terms of the what versus where pathways, well, I mean, I'm sure you know this better than I do, but it's not really a where pathway, right? Like from the, more or less as soon as this was proposed, it became like the what and the how-to pathway or the action pathway. And it turns out that actually the action pathway also has slightly objects and things like that. I think if you look at the aphasias that you're describing, I think it makes perfect sense that in the same way that, and again, taking a page just from the engineering, right? So like the engineers say, like if you're creating a simulation, you have an entity, and we have to split up really early on the entity in terms of like the thing that needs to get rendered out in front of the camera, the shape, and the thing that actually matters for tracking and things like that. Now, they're doing that in order to produce a reasonable simulation in real time. Reverse the process. You get two streams, the physical tracking stream and the thing that is the inverse rendering, the thing that cares about the what and the thing that cares about the physics, right? So I think that there's an argument to be made that the dorsal pathway is that thing, the body and the carrier of the body and things like that. And when you look at the aphasias, right, like you ask someone, what is this? And they say, I don't know, right? Like exactly the thing that you were describing. But imagine a system that was placing something like a rough body around it. It knew that there was a rough body there. For the purposes of throwing it or catching it or putting your arms around it, you know more or less where it is. But what is it? Could be a pen, could be a laser pointer, could be a frozen gecko, I don't know, right? Like there's just some hole there that is roughly cylindrical shaped. Right? So I think, yeah, that's would be my argument. I think it makes sense of aphantasia, by the way, as well.
I want to ask about the notion of a simulation and tying it to naive physics. In that some people think that for social relations, we simulate other people in our minds and what they will do, and that's how we understand other people. Is that a different use of the word simulation, or how are they related?
Sadly, yes. So there are, I'm sure you know this, there are these arguments, so a lot of this focus on intuitive physics, but there's all these arguments about intuitive psychology. So in the same way that we understand, the behavior of everyday things, how do we understand the behavior of everyday people? And there's lots of works on trying to capture that. And within that, there are these two huge camps about theory and simulation theory. And there, simulation theory is about the suggestion that, we have this box that is how we are, never mind, is how we ourselves make decisions. And when they say simulation, they mean we run the simulation of us making a decision. And that's how we understand it. We mean it more in the sense of inverse planning. So we have a separate box for reasoning about other people that doesn't require us to run a simulation of what we would decide. But we are running something like a planning process. To the degree that you're reasoning about a planning process as a simulation, it would be that. So there are analogies there. Unfortunately, the word simulation is overloaded in that context.
I mean, I think some people think it might be a similar mechanism. And you've said we don't simulate what we would do, but actually,
Sorry.
to understand another person, you actually, maybe it's the case you are simulating what you would do to infer what they would do.
So sorry, I was too glib and I said that we don't. That was wrong of me. There are titanic struggles about this thing. And what I meant was that I'm in the camp that thinks that we're using theory and inverse planning. That's not to say that there are people arguing that we simulate that.
Thank you.
Sorry, Philip, I keep doing time check because I'd love to keep talking, but I also want to leave time for discussion.
Yeah, I think we're so close to the end that I propose we just continue this discussion. We'll have more time for discussion in future days. So I think we just continue on. Right. And feel free to raise points from other talks too. But yeah, go ahead. So
Okay, sure.
Really, really awesome talk. I especially like this last thing about how many things we can simulate. So I have a question for you. Suppose that we had a setting more similar to the previous talk, where you had a ball falling down, hitting an object, and could probabilistically go one way or the other, and you want to track that. Do you think that you would basically have to either commit to one track, or like track the superposition of both of them and like go back and forth between them?
This is a great question, and since we're in discussion phase, like Toby, do you have a sense for that?
I think you would be committing. Like, so at least in the eye tracking data, what we see is that kind of commitment, right? In the eye tracking data, when we ask them, basically you can see them basically simulate their eyes. And in that case, at least, they are then, they might be going one time and going the left side of that obstacle, and the next time they're going the right side of that obstacle. So it's still this kind of serial process. So my sense would be